Hi everyone, this is Mrs. GA, and today we're going to be finding complex solutions for polynomial equations. Before we get started, I have a quick warm-up for you guys, so please pause the video and give it a try. Hit play when you're ready to check your answers. Alright, go ahead and check your work here. So here's the possible m values, factors of our coefficient, or of our constant, and here's the possible n values, which are the factors of our leading coefficient. So all of the possible combinations of m over m would be 1 over 1, 3 over 1, and then 1 over 2, and 3 over 2, and all of those are plus or minus. So you could try any of those 8. If you try -1, you'll get a remainder of 0. And then this remaining polynomial is 2x squared minus x minus 3, which is factorable. And you get these as your final factors. So your zeros would be -1 and positive 3/2. And -1 has a multiplicity of 2 because the factor is squared. So today we are going to be finding all possible zeros for our polynomials, meaning we could have some real answers or we could have some complex and imaginary answers. So that leads us to what's called the fundamental theorem of algebra. So the fundamental theorem of algebra states that every polynomial function with a degree of n, as long as n is greater than or equal to 1, has at least one zero, where the zero may be real, including rational and irrational numbers, or complex. So every polynomial has at least one zero, and again, it might be real, it might not be real, it has at least one zero. So a corollary to that is actually, I think, just as useful, if not more useful in terms of application. Every polynomial function with a degree of n greater than 1 has exactly n zeros, including complex numbers and multiplicities. So the degree of the overall polynomial tells you how many answers to expect when you're finding the zeros. But again, that could include imaginary answers, and it includes multiplicity. So like in the warm-up, although it looked like we only had 2 answers, -1 had a multiplicity of 2, so we would count it twice. Okay, let's give one of these a try together. So we're going to do whatever we need to do to find all of the possible roots. So of course, if we can solve this by factoring, that's definitely the easy way to go. First thing to note is that there is a GCF of 2. So we can just divide 2 on both sides. Let's just divide it out all together. And that leaves us with x cubed minus 6x squared minus 17x plus 102 equals 0. And then if we can factor, again, we should try to factor. In this one, since there's 4 terms, let's try factoring by grouping. So if you group the first 2, my GCF is x squared. And if you group the second 2, the GCF is -17. And then you see, oh, we can factor this by grouping. It's x squared minus 17 times x minus 6 equals 0. So you don't always have to go straight to that rational root theorem. Always check to see if the polynomial is factorable. Now, since we factored as much as we can, now we can do the zero product property. And remember, since the degree of this polynomial is 3, we should expect 3 roots for this polynomial. So we should have 3 answers. So if you take this first factor and set it equal to 0, we can finish solving this with the square root method. So isolate your squared term and then take the plus or minus square root of both sides. It's really important to remember the plus or minus because if you forget, then you're going to be missing one of your answers. So this is actually 2 of our zeros, and then our other factor gives us our third 0 of 6. So our answers are positive 6, positive root 17, and negative root 17. And of course, we can write these as plus or minus root 17. I just listed it out like this to show you that there are, in fact, 3 zeros to this polynomial that has a degree of 3. Now, this one is a real rational 0. These are both also real zeros, but they are irrational zeros. All right, let's try another one together. So this one, again, we don't always need to jump straight to that rational root theorem. We should see if we can factor it. And this is a quadratic-type equation. because this degree here is double this degree. So to factor something like this, you may be able to just do it in your head, pretending that this was just a quadratic equation, or we could do it the more formal way. We could actually use substitution. So let's say we replaced our x squared with just u. So then that would make this equation into u squared minus 6u minus 27 equals 0. So now it's a quadratic equation that we can factor. So it becomes u minus 9 times u plus 3 equals 0. And then once it's factored, we can substitute x squared back in. So that would give us x squared minus 9 times x squared plus 3. So now we have our first two factors of our polynomial, but we should always check to see if we can factor more. This first one, x squared minus 9, is difference of two squares, so we can factor more here. But this x squared plus 3, we can't factor that more, so we'll just leave it. So now our polynomial is completely factored, and we could do zero product property. So this first one, it gives us a solution of -3. Our second factor gives us a solution of +3. And then this third factor, if we do the square root method, you can see that we'll get two imaginary solutions. So we get x equals plus or minus I root 3. So if you look at the degree of the polynomial, again, the degree is 4. So we should expect 4 answers. So we have 1, 2, 3, 4. So 2 of them are real and 2 of them are imaginary. So let's just list out our zeros really quick. So we have -3, +3, positive I root 3, and negative I root 3. And again, you can absolutely write this as plus or minus I root 3. That's completely fine. This is just to show that there are 4 roots to this polynomial that has a degree of 4. All right, so go ahead and try this one on your own. Pause the video while you give it a try, and then hit play when you're ready to check. All right, go ahead and check your work here. So this you can factor using the difference of two cubes formula. So this factor, 2x minus 3, gives us one real solution, 3/2. And then for this remaining factor, we can actually finish solving using the quadratic formula. So as long as one of your factors is, or if you can get your factor down to a quadratic, you should always, always, always be able to solve. Even if it's not factorable, that's okay. We know other ways to solve quadratic. So in this one, you do need to do quadratic formula, and you get two imaginary solutions here. So I do have 3 zeros, which matches the degree of our function. 1 is real, and 2 are complex. All right, let's try one more together. So here we're finding the zeros, so let's set our y value equal to 0. So the first thing you should always check for is to see if you can factor. So here you can factor out a GCF of x. So let's do that first. One thing to note, if your GCF is a value, you can just divide both sides by that value. However, if your GCF is an x, you can never, ever, ever divide out the x. Like, you can't divide both sides by the x because, well, one, you don't know what x is. X could be 0, and we know that we can't divide anything by 0. So that's one reason. But also, we know that with every factor, there's an answer trapped inside. So if you just divide it out completely, you're losing that answer. So this does give us an answer, a root of 0. So make sure if your GCF has a variable that you don't lose the variable along the way. So now this, we do need to finish solving. Here, there's no way for us to factor, so we do need to use that rational root theorem. And again, I'm just using it for this remaining polynomial here. So our possible zeros would be plus or minus 1, plus or minus 7, plus or minus 13, and then plus or minus 91. So we have 8 possible options. So we are just going to start checking these with synthetic division. Let's check. I'll set up my synthetic division here. And again, I'm just going to be using the coefficients from this reduced polynomial. So we have 1, negative 13, 55, and negative 91. So let's check 7. Drop your first number. 7 times 1 plus negative 13 would be negative 6. 7 times negative 6 plus 55 gives us positive 13. And 7 times 13 plus negative 91 is 0. So that gives us, it tells us, since the remainder is 0, that 7 is one of the zeros. So now we have another factor. We still have the factor of x. We have the factor of x minus 7. And then our remaining polynomial is x squared minus 6x plus 13. So this is a quadratic, so even if we can't factor, we know we can finish solving. And for this one, we will need to do quadratic formula to finish solving. All right, let's go ahead and do that. So here we have x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a, x equals 6 plus or minus the square root of. Here we do get a negative radicand, but that's okay. We know how to finish simplifying. So here x equals 6 plus or minus 4i over 2, which since both of these terms are divisible by 2, we can rewrite as 3 plus or minus 2i. So again, looking at the degree of our polynomial, we should expect 4 answers. So if you look here, we have 0 as one of our answers, as one of our roots, positive 7, and then we have 3 plus or minus 2i. So 3 plus 2i is one of our roots, and 3 minus 2i is our other root. So we do have 4 zeros. 2 of them are real, 2 of them are imaginary. So now we're going to be kind of doing the opposite. We're going to see if now we can actually create the polynomial function if we are given it 0. So we're going to work our way backwards. So for these, we do need to know 2 really important theorems, the irrational root theorem and the complex conjugate root theorem. So what the irrational root theorem says is if your polynomial has the irrational root a plus b root c, and where root c is the irrational part, so a radical that is fully simplified but doesn't come out to be a nice integer, if a plus b root c is one of your zeros, then a minus b root c is also going to be one of your zeros. So those irrational roots will always come in pairs. So it's going to be a plus or minus b root c. So sometimes you'll only be given one of the zeros, but you have to know if this zero exists, so does the other one. So you automatically have that second zero. And then the complex conjugate root theorem is very similar to the irrational root theorem. If a plus bi is one of the roots of your polynomials, then a minus bi is also going to be a root. So you might have noticed in all the examples we did, anything that had an irrational answer always came with 2 irrational answers. You never just got 1 irrational answer. And anything that had an imaginary answer always had 2. It never just had 1. So they always, always, always come in pairs. So we definitely need to know both of these when we are writing our polynomial functions, because again, it tells us what one of our zeros could be. All right, so let's try one of these together. So we're going to be writing the polynomial function with the least degree possible and a leading coefficient of 1 that has these given zeros. So we're told that one of the zeros is 5, and then one of the zeros is 3 plus 2 root 7. Well, we know that if one of the zeros is 3 plus 2 root 7, we also have the second zero, or our third zero, I guess in this case, of 3 minus 2 root 7. And that's that irrational root theorem. So there's the 3 zeros that we know. So we're going to write the polynomial with this degree of 3. So we're going to set up the factors. And I just want to remind you, when we're creating our factors, we always do x minus our 0. So we have x minus 5, then we have x minus, and then the 0, so 3 plus 2 root 7. And it is really important to put that in parentheses because we're subtracting the entire 0. And then we have x minus 3 minus 2 root 7. So now here it's really just a matter of multiplying these out. I do have a little trick for you guys when you are multiplying it out. So just to make it a little easier, you don't have to do this, but it could save you some time. First, I'm going to distribute those negatives, so x minus 3 minus 2 root 7, and x minus 3 plus 2 root 7. So actually, if we kind of group x minus 3 as its own factor, when we go to multiply out these two polynomials, it will actually save us a little bit of time. So you'll see what I mean in just a second. So again, I'm going to, just to show, I'm going to group the x minus 3 as its own factor like this, and then we have minus 2 root 7, and then I'm going to, again, group this x minus 3, and then plus 2 root 7. So I'm going to multiply out these two polynomials first. We'll multiply in the x minus 5 later. So when I do this, I'm going to treat x minus 3 as its own term. So I'm treating this, pretend this is just a binomial times a binomial. So I'm going to do x minus 3 times x minus 3. So that gives us x minus 3 squared. And then I have x minus 3 plus 2 root 7. So it's going to be plus 2 root 7 times x minus 3. And I'll just write it like that temporarily, because here in this step I have minus 2 root 7 times x minus 3, which they will cancel out. And then in this last step, we have negative 4 times 7, so negative 28. And again, here, since we have plus 2 root 7 times x minus 3, minus 2 root 7 times x minus 3, they cancel out. So it makes it a little bit quicker for us to multiply something like that out. So now we still need to multiply out this binomial. So x squared minus 6x, and then we have plus 9 minus 28, so minus 19. And then we just have to multiply out these two final polynomials here. So x cubed minus 6x squared minus 19x minus 5x squared plus 30x plus 95, and that leaves us with x cubed minus 11x squared, and then plus 11x plus 95. And here is our polynomial function. So again, if you want, it can be helpful to group these common factors here and then treat this as a binomial times a binomial. However, if you just would like to multiply this out as a trinomial times a trinomial, you'll end up with the same answer. It might just look a little uglier. So notice again in the directions it said the polynomial function with the least degree, so it means like these are the only 3 zeros, we don't need to add any extra zeros in, and the leading coefficient is 1. So for that a value, we don't need to solve for that a value, we're just going to assume it's a 1. So this is our polynomial function. Okay, let's try another one together. Same set of directions, so we're given the zeros 2, 3, and 1 minus I. So remember that second theorem that we learned said that if a plus bi is a 0, so is a minus bi. So here we have 1 minus I is one of our zeros, so we know that 1 plus I must be an additional 0. So here we're going to make this polynomial function with these 4 zeros. So let's start by setting up our factors. So x minus 2 times x minus 3 times x minus 1 minus I in parentheses, and then x minus 1 plus I. And then we can distribute the negative in the third and fourth factors. And again, when I do that, I'm going to want to group this x minus 1 as its own term, and then we have plus I, and then here we have x minus 1 minus I. So when I multiply these out, I'm going to treat this like a binomial times a binomial. So here, let's see, I'll do these two. I'm going to multiply these two binomials and then multiply these two binomials. So we have x squared, and then we have minus 3x minus 2x, so minus 5x plus 6. And then here we have x minus 1 squared. That's x minus 1 times x minus 1. And then here we have negative I times x minus 1 plus I times x minus 1. So those will cancel out. And then all I have left is negative I squared, which is just plus 1. All right, let's continue simplifying. So x squared minus 5x plus 6 times, when we multiply out this binomial, we should get x squared minus 2x, and then we get plus 1, which gives us plus 2. And then from here, it's just a matter of multiplying out these two trinomials. So you do need to be very careful. Okay, so let's multiply it out. So we have x to the 4th minus 2x cubed plus 2x squared minus 5x cubed plus 10x squared minus 10x plus 6x squared minus 12x plus 12. And then here, when we combine like terms, we should end up with x to the 4th minus 7x cubed plus 18x squared, and then minus 22x plus 12. And there you have it. So again, knowing that little trick of grouping the x minus 1s and then treating these like binomials might save you a little bit of time, but it's definitely not required to end up with the same answer. All right, I have this last example for you to try on your own, so please pause the video and give it a try. Hit play when you are ready to check. All right, go ahead and check your work here. So again, if 2 plus 3i is a 0, so is 2 minus 3i, and if 4 minus 7 root 2 is 0, then so is 4 plus 7 root 2. So here's your 4 factors. Again, you can distribute the negatives, and then I would group the x minus 2s and then the x minus 4s. So when you multiply these first two, treat it as a binomial times a binomial, giving you this. And also remember that I squared is -1. So here you get -9i squared, which is plus 9. And here again, it's a binomial times a binomial. So you get x minus 4 squared and then minus 98. And then this you should multiply out to get this trinomial. This you can multiply out, combine like terms to get this trinomial. And then it's just some more multiplying. So again, here there's a lot of chances to make small mistakes along the way. So just take your time and be careful. And then this should be your final answer. Okay, that is all for today's video. Thank you so much for watching.